So this will be a brief description of manometers, which are really important in hydraulic engineering. And just to review the concept of force, how it's related to pressure. In this case, this is the shear stress, which is a sort of same units as pressure, but it's shear times the area. So force divided time area. And then whenever we have normal stress, which is pressure as well, then the notation that you're used to, it would be sigma, force over area. Of course, we measure pressure, and it's a normal force exerted by a fluid per unit area, and you can have several units, and we will see in the lab some pressure gauges. Now, there's two things that are really important, and it's to understand the definition between absolute pressure and gauge pressure. And of course, the gauge pressure could also be a vacuum pressure. So the actual absolute pressure is the actual pressure at a given position, whereas the gauge pressure is the difference between the absolute and the local atmospheric pressure. Most pressure measuring devices are calibrated to read zero. So what happens is that for atmospheric pressure, if you have a gauge meter, it will not read the atmospheric pressure, but the actual pressure inside that container, excluding the atmospheric pressure. A vacuum pressure would be, of course, below the atmospheric pressure. So 1 atmospheric pressure, 1 atmosphere, that's how we call it. So let's see the easiest case, which would be this. Here you have your atmospheric pressure and then a gauge pressure. So if you add them, you have the absolute pressure. So in that case, whenever you have a P absolute, of course, you'll have absolute pressure that it's equal to gauge plus atmospheric, and you have your P abs larger than your atmospheric pressure. Now, in the case of a vacuum pressure, what happens is that it's less than atmospheric pressure. So here is your atmospheric pressure, and now the vacuum pressure is going to be less. It's like a vacuum cleaner. We talked about that. Now, in our definition that I wrote here, what happens is that if the gauge pressure is negative, then your absolute pressure is going to be a negative value plus the atmospheric pressure. And so now it's this equation here. So all you have to remember is that vacuum pressure is a negative pressure, because it'll be less than atmospheric. I hope that quick description helps. So we know already the pressure of water with depth is rho GH, and this seems kind of redundant at this point, but you'll see how whenever we deal with manometers, these can get confusing. So here is our pressure, and as we go down below the surface, the pressure increases as the depth increases in this case. Okay, so but you go down and pressure increases. Okay? Whenever we look at pressure and how it changes with depth, then we know that at a given depth the pressure will be constant. So it doesn't matter the shape or form of the container, as long as you have the same fluid, the pressure will be constant at a constant depth. So you have here at the surface atmospheric pressure, and then this would be your absolute pressure. It would be the atmospheric plus the gauge. So this here really is the gauge pressure. Or one thing is, let me erase this. Whenever we have different shaped containers, sometimes we think that the pressure will change, but that's not the case. Okay, so whenever we look at this situation, here you have PA, and it's at the same level, but you have the same fluid on top, so the pressure is the same. Here you have the same pressure, here you have the same pressure, same pressure, same pressure. If we have a different fluid, it's not the same. So like here, H and I are at the same level. Here I have mercury, and here I have water. So the pressures in H and I are not going to be the same. Okay? So if you have a manometer, a simple manometer used to measure average temperatures, so we have here your P atmospheric, and then here you have your H, so you're going down in depth, so it's P atmospheric plus raw GH. And then whenever you come here, on this side is the same pressure, right? And then here you have the P gas, and it's a gas, so the pressure is all the same. So this would be the pressure that the gas exerts. Now, reviewing the same concept, what I'm going to do is, let's go from point 1 to point 2 to calculate either P1 or P2. So I have P1, and now I'm going down here. So I say, okay, times the specific weight of the water times H1. And remember, so here is water. I have the same pressure as here. Now, if I have the oil now, which is here, is going to be the same pressure as here. So this here in the interface is almost the same pressure. I'm going to assume it's exactly the same. So now I'm going down. So now, of course, I add pressure, and in this case, I have oil times H2. And then now I'm here in the interface, and I'm going up. So, and this is mercury. So it's the density, a specific weight of mercury times A3, and this is going to be equal to P2. It doesn't matter if you go from left to right or from right to left. You erase and go from the other position. So now I say, okay, P2, and I'm going down plus, and it's mercury, so mercury times H3. So now here the pressure is the same, but I'm going to go up, and this is H2, but it's this oil, so I'm decreasing in depth, so it would be minus E oil times H2. So now I move here. I already used H2, the depth I only use once. Now I'm going to go up in the water plus gamma water H1, and that's going to be equal to P1. So I can calculate P1 or P2, and then the other thing is that if they ask for P1 minus P2, then of course use either one of those definitions. For example, I say P1 minus P2 equals gamma mercury H3 minus gamma oil H2 plus gamma water H1. So sometimes you don't have to know specifically what's P1 and P2, but you know the difference. Now here I have P1 minus P2, so if I get this value here and I get a positive value, then P1 is larger than P2. But if I get a negative value, then I know that P2 is larger than P1 if I have negative. Okay? The manometer is also used to measure pressures across a flow section, and that comes from the manometer. So in this case, from point 1 to point 2, what you have is differences in elevation. You have A and H. You look for those differences, and then you have, in this case, liquid 1 and liquid 2, which we usually use mercury. So the expression then it's P1 plus the density 1 G8 plus H. In this case, we went from P1 and went all the way here, and then you go up, and it's this expression minus, and then you go up again, and this is the minus. And then whenever this expression is simplified, the difference in pressure is going to be rho 1 minus rho 2, or rho 2 minus rho 1 times the H. But it's the same principle. So I want to go over a review of hydrostatic forces on plates. In thermofluids, you probably saw plates that are horizontal and vertical. So I want to review this and then add a little more of the curved surfaces that are so important because a lot of valves and gates can be curved. So we know that at a specific depth, the pressure does not change. So like in this case, you have the same fluid on top, and this is the pressure. The gauge pressure would be then rho GH. So whenever we're talking about the force is the pressure times the area. So here we have the area of a plate if it's A times B. So then we have resultant force. And so this is the magnitude of the resultant force. We will use a two-dimensional approach, keeping in mind that it's a prism, really the pressure, but we'll always be using a two-dimensional approach like you did in statics. And what we'll look is at submerged plates that are vertical, and it can be a plate or it can be a wall. What's important to recognize is that the pressure, the hydrostatic pressure, which is due to water, even if the wall is very, very high, the hydrostatic pressure starts where the water starts. So this is 0, and you have a triangular, and this is like a line, P equals rho GH with intercept equals 0. So if you look at the form of this equation, M x plus b, so this is the slope. And this is your x, and then 0 intercept. So there's two questions. What is the magnitude of the resultant force and where it is located? Okay, so the pressure is rho GH, but how do I calculate the magnitude of the resultant force? That's an important question, because here is all the pressure, not the average force. And this resultant force, what the magnitude and the location is two different things. So let's talk about the magnitude. The magnitude I calculate pressure at the centroid of the plate. Okay, in this case is the wall. So here I have my wall, and if I have this h distance, I will calculate the magnitude at h over 2. But the location of that resultant force is not there. The location, you have to look at the centroid of the distributed load. That's where the resultant force is located. So this goes back to your principles in statics. This is the triangular distributed load, and they said, well, where is the resultant force located? Well, it's located, in this case, let me delete this. And then this would be, if it's h, it would be 2/3 of h and 1/3 of h, because that is where the resultant force would be located. Okay, so the location of the center of pressure is this, and this is yp. Okay, and that is not the same as the centroid of the wall. You look at the centroid of the distributed pressure. Okay? So this is for a triangular. What is the magnitude? And then where is the centroid of the wall is a different story, right? And where the location of the center of pressure is different. So you calculate the resultant force at, here in this case, you have H, so it's going to be raw GH, centroid of the wall, and then from there I get my average force, which would be pressure times the area of the wall or the plate. The location then is at the centroid of the distributed load. So this is my resultant load, but the location. Okay. If you have a vertical submerged plate, it's just like the wall, but then remember, if you have water on both sides, then it's zero. Law of action reaction. So that's why whenever you're submerged in a car, I hope you never find yourself there, and the car is full of water, then there's no pressure. You can easily open the door. Okay? In your book, there's some surface area, centroid, and moment of inertia for simple geometric plates. And we'll see how those are used. And so the first case we saw was whenever the plate was submerged, but right at the surface, and now we have a distance s. If we had the initial case, then it would be like this. But as I mentioned, now we have a plate submerged at a distance s. So that changes the profile of the pressure. So we have still the same notation, P, and then in this case we have a plate of height B. So the resultant force you calculate at the centroid of the plate. So when I look at the centroid of the plate, the pressure at the centroid of the plate would be S, or the pressure at S plus pressure at a distance, then I need to add S plus, well, I already put the S, so let me erase here, plus the pressure at B over 2. Okay? So the pressure would be, the gauge pressure would be raw G S plus V over 2, which would be here. So the force, the resultant force, would be that pressure divided by the area of the plate. Let's say that this is B and has a width A. The location of that force is different, the pressure point. So this is located in a different place, and that's what we'll see how you can calculate that. Okay, so the magnitude of the resultant force is equal to the product of the pressure at the centroid of the plate times the surface area of the plate. But the location is not the same. It's at the center of pressure, and that's what we'll need to calculate. What is that YP? Okay, so we'll call YC the location to the centroid of the plate, and YP the location of the center of pressure. Okay, so we have already calculated this, the resultant force at the centroid. And then for a rectangular plate, we have to, or for any plate, we have to look at the second moment of inertia. And if this is a rectangular plate, this is the second moment of inertia. You need to look at the equation that you're using, because in this case, here the width is A and the height is B. So it's A, B to the third. If you have it reversed, you need to keep an eye on that. So the location of the center of pressure would be the location of the centroid of the plate plus the second moment of inertia around the centroid divided by yc times a. So that's as easy as that. What you need to remember is that if you do your calculations and you get a yp lower than yc, it's not possible because it's always yc plus something else. So in summary, this would be the hydrostatic force. You calculate the magnitude at the centroid of the plate. The location is yp, and this is the equation you use, and this is for vertical plates. This is an example from a previous book. It's important that you remember this is from thermofluids, so review those concepts. In the case of a horizontal plate, you don't need to calculate yp because this is the location of the centroid, and yp is the same because it's based on the depth. The pressure on inclined surfaces. So the concepts here are not going to change, but now you have to look at an angle. So we have, we call now here HP and HC, and what was YP and YC is from the surface to the centroid and to the center of pressure, but it's at an angle. The pressure you don't calculate at this distance YP or YC. You don't use this YC. You use this because for hydrostatic pressure is based on vertical height. So HP, and this is your angle here, is YP times sine of zeta, and HC is YC times sine of theta. So that's what you need to keep in mind. But it's the same process. So now for a submerged tiled rectangular plate, so it's at an angle, the YP equals the YC, and of course you calculate this part here, so the height of the centroid based on, this is always half of the length, plus whatever distance you have, and now you have an angle, so you need to incorporate into your equation the expression for sine of theta. Okay, so it's important to recognize that. Now, for hydrostatic forces on curved surfaces, you have several options and several other additional steps. In the case of a curved surface, like you have here, let's say that this is your curved surface. There's two things, and I'll delete this for a moment. There's two forces. There's a vertical component, which is the weight of the water on top of this surface. And then, of course, there's the horizontal component from the pressure from the water on the side. So you have here this weight because it was cut into two pieces, and then this. So you have a vertical and a horizontal. So anytime you have a curved surface, you look at the water, at the weight of the water on top, on the vertical, that is your vertical component, and then the pressure on the side. And so the resultant force would be something, well, actually coming from this direction, that would be the resultant force, and it's following the same as in statics. So you have a horizontal and a vertical component, and then you have an angle, and then the resultant force. If you look at example 2.5 on page 28, it's very well explained. I don't think I can do a better job at explaining it. If you have questions, send me an email. But make sure that you practice that example, because also the homework problems will include some of these concepts. Thank you very much.